Hello everyone, today we're talking about null space and column space again, and we're going to discuss a connection to transformations. So I think I'll start off just with a big example. So let's take a matrix A to be a 3 by 4 given by the following. Minus 2, 7, minus 8, 1, 3, 6. This is a 3 by 4 matrix. And let me give you a couple of vectors. Let's take U to be 3, minus 2, minus 1, 0. And V, let's be the vector 3, minus 1, 3. Okay, so the question I want to ask, which is typical in the homework and discussions we've had, is the vector U, or let's say V, in the null space of A? And is the vector U, or let's say V, in the column space of A? And so maybe before I answer those, let me just recall what these things are. So recall, the null space of A is by definition the solution set of a certain system, the homogeneous system AX equals 0. Okay, and so this is by definition, anything that's in the null space will have 4 entries because you have 4 variables. And in particular, this is a subspace of R4 in this case, whereas the column space of A is by definition the span of the columns of A. And we saw last time, well, in general, when you have the span of a bunch of columns, that's going to be a subspace of, the thing that the columns live in. In this case, it's going to be R3. So right away, I can eliminate a couple of these questions, right? So when I ask, is U in the null space of A? Well, that's possible because it has 4 coordinates, but notice that V, has just the wrong number of entries. It has 3 entries, so it's no way it's going to live in R4. And similarly, since the column space consists of things in R3, there's no way that this vector U can be living in the column space. Okay, so just the first thing to check is, are your dimensions, the number of entries, are they matching up to what they should be? Now, let's answer the remaining questions. So to check if U is in the null space of A, we want to make a calculation. We just compute what is A times U. So in general, if you want to know if a vector is in the null space of a matrix, you take A times that vector. So I won't do it for you here. I'll spare you the details. But if you take A, that's given up here, and you multiply it by U, what you get is, in this case, the first entry is 0, but the second entry, it turns out, is minus 3. So again, if you take A times U, you'll see that the second entry, taking the second row, dotting it with the vector U, you get minus 3 in the second entry, which means I don't care what's in the third entry. This is not the 0 vector, which tells me that U is not in the null space of A. Okay, so that answers the kind of remaining question on this side. There's one more question to ask. Is V in the column space of A? So let's see. To check if V is in the column space of A, so in general what you're going to do is you're going to solve a system where you take that matrix A and you augment it with V, okay? And all you need here is the echelon form, because you want to know if this system is consistent. So let me do that. I'm going to, again, spare you the details here. But what this reduces to is something like this. So one of the echelon forms is 0, minus 1, 5, 4, 2, 0, 0, 17, 15. So again, all I did here is I took this matrix A you gave me, augmented it with V, and then it reduces to something like this. Notice the pivots, the pivots are there, and in particular, this doesn't have any row of zeros with a non-zero thing, so this is consistent. And if you have a consistent system, that means that that vector that you augmented with is indeed in the column space of A. And so, that's again how you kind of check. So questions like this, if I give you vectors and I want to know are they in the column space, null space, that's how you do it. Now, let me just remind you, to actually describe the null space, we would need to reduce to reduced echelon, because, if I want to describe the null space, I want to describe the solution set of the homogeneous. So again, this would be to describe the solution set of AX equals 0 of the homogeneous. And let me just kind of show you how that works again, sparing you the details of the calculations. So if you took this matrix and you reduce further to reduced row echelon, it's going to look something like this, assuming I did everything correctly. Well, we know where those pivots are, and they turn out to, well, to give you the reduced echelon form that looks like this. And, you know, then this would then tell you, I'm going to not go through this here, but as usual, you would take this reduced echelon form and describe the solution set of the homogeneous, right? You'd have 4 variables here, and you do the usual thing. So just kind of an observation I want to make here. Note that the null space of A is hard to describe in the sense that you need to make, you know, lots of row operations to get to a description, but it's easy to check if a given vector x is in the null space. So like we saw before, right, if I wanted to know if something was in the null space, I just look at A times that vector. If it's 0, it's in. If not, it's not in. But describing the null space is a little bit of a pain because we have to go through all these row operations, describe the solution set in vector parametric form. Now, column space is kind of the other story, right? Column space is easy to describe in the sense that it's just the, right, just the span of the columns, but it's hard to check, let's say, if a given, let's say, B is in the column space of A, okay? So, you know, again, the column space by definition is just the the span of the columns here. And to actually check if something was in there, I had to row reduce, right? So here's where we checked if V was in the column space. I had to actually go and row reduce. I only had to go to echelon, which was nice, but I still had to do something. So that's kind of how the null space and column space kind of compare and contrast. The last thing I want to do on this lecture is talk about how this stuff relates to transformations. So now a connection to transformations. And let me just, well, I'll give you guys a definition. So definition, suppose we have a transformation that eats vectors in Rn, spits them out in Rm as usual, and suppose this is a transformation. So let me draw my usual cartoon. We're starting in Rn. I take a vector x, and it goes somewhere into T of x, right? So and that lives in Rm, of course. So it eats vectors in Rn. I apply the transformation T. It spits out a vector in Rm. So the definition, first of all, is that the kernel of T, of this transformation T, is the set of vectors x in Rn such that T of x equals 0. So in a more mathy kind of way to say this, the kernel of T equals the set of x in Rn such that T of x equals 0. Okay, that's one notion that I can, you know, subscribe to. The notion of any transformation gives rise to what's called the kernel. On the other hand, you also have what's called the range of T. So this is the set, by definition, the set of vectors, let's say y, in Rm now, of the form y equals T of x for some x in Rn. So, you know, what this is saying is that it's all the vectors on this right-hand side, all the vectors over here in Rm, that get hit by the transformation. And so another kind of mathy way to say this would be it's the set of y in Rm such that y equals T of x for some x in Rn. Okay? And again, you know, the way to think about this is the kernel is all the stuff over here, you know, that gets sent to 0. So all the vectors in Rn that get sent to 0, that's going to be the kernel. of T. It's all the things on this left-hand side, all the vectors in here, that get sent to the 0 vector. Right, that's the 0 vector here. Whereas the range is all the stuff over here that come from, right, the left-hand side. So the range would be everything, actually it includes that vector there that I drew. The range would be everything on this right-hand side that comes from something. So it's possible that there are some vectors in Rm that don't come from anything in Rn, via this transformation. Those are not in the range. So the kind of main thing I want to point out now is, note that if T is a linear transformation and defined by a matrix, let's say an M by N matrix A, so that the transformation T of x is given by matrix multiplication, then these things, these abstract notions of kernel and range, are actually things we know and love, right? The kernel of T, well, remember, by definition, that's the set of vectors x such that the T of x equals 0, the 0 vector. Well, in this case, it's the set of x such that A times x equals 0, because we're assuming this is a linear transformation. And that has a name, right? So the set of vectors that gets sent to 0 by matrix multiplication is called the null space of A. That's what we just were talking about. And on the other hand, the range of T, so this is, by definition, the set of y such that T of x equals y for some x, right? And, well, if we're in the world of matrix multiplication, this is the set of y such that ax equals y. In other words, the set of if you like, right-hand sides where ax equals that thing is consistent. And of course, that has a name that we've been studying, right? This is the column space of A. Okay, and so the point here is that when you have a transformation, any transformation gives rise to these abstract notions of kernel and range. When your transformation is just matrix times the vector, right? When it's a matrix transformation, the kernel is just the same as the null space. The range is just the same as the column space. So it's yet another way to think about these concepts in the setting of the more abstract context. Okay, that's it for now. We'll see you next time.